where does all this stuff come from? This rock, that cow, your heart. Not the things themselves, mind you, but what they're made of, the atoms that are the fabric of all things. To answer that question, we look to the law of conservation of mass. This law says, take an isolated system, defined by a boundary that matter and energy cannot cross. Inside this system, mass, aka matter and energy, can neither be created nor destroyed. The universe, to the best of our knowledge, is an isolated system. But before we get to that, let's look at a much smaller and simpler one. Here we have 6 carbon atoms, 12 hydrogen atoms, and 18 oxygen atoms. With a little energy, our molecules can really get moving. These atoms can bond together to form familiar molecules. Here's water, and here's carbon dioxide. We can't create or destroy mass. We're stuck with what we've got. So what can we do? They have a mind of their own. Let's see. They've formed more carbon dioxide and water, 6 of each. Add a little energy, and we can get them to reshuffle themselves to a simple sugar and some oxygen gas. Our atoms are all accounted for, 6 carbon, 12 hydrogen, and 18 oxygen. The energy we applied is now stored in the bonds between atoms. We can re-release that energy by breaking that sugar back into water and carbon dioxide, and still, same atoms. Let's put a few of our atoms aside and try something a little more explosive. This here is methane, most commonly associated with cow flatulence, but also used for rocket fuel. If we add some oxygen and a little bit of energy, like you might get from a lit match, it combusts into carbon dioxide, water, and even more energy. Notice, our methane started with 4 hydrogen, and at the end, we still have 4 hydrogen, captured in 2 water molecules. For a grand finale, here's propane, another combustible gas. We add oxygen, light it up, and boom, more water and carbon dioxide. This time we get 3 CO2s, because the propane molecule started with 3 carbon atoms, and they have nowhere else to go. There are many other reactions we can model with this small set of atoms, and the law of conservation of mass always holds true. Whatever matter and energy go into a chemical reaction are present and accounted for when it's complete. So if mass can't be created or destroyed, where did these atoms come from in the first place? Let's turn back the clock and see. Further, 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 too far. Okay, there it is. The Big Bang. Our hydrogen formed from a high-energy soup of particles in the 3 minutes that followed the birth of our universe. Eventually, clusters of atoms accumulated and formed stars. Within these stars, nuclear reactions fused light elements, such as hydrogen and helium, to form heavier elements, such as carbon and oxygen. At first glance, these reactions may look like they're breaking the law, because they release an astounding amount of energy, seemingly out of nowhere. However, thanks to Einstein's famous equation, we know that energy is equivalent to mass. It turns out that the total mass of the starting atoms is very slightly more than the mass of the products, and that loss of mass perfectly corresponds to the gain in energy, which radiates out from the star as light, heat, and energetic particles. Eventually, this star went supernova and scattered its elements across space. Long story short, they found each other and atoms from other supernovas, formed the Earth, and 4.6 billion years later, got scooped up to play their parts in our little isolated system. But they're not nearly as interesting as the atoms that came together to form you, or that cow, or this rock. And that is why, as Carl Sagan famously told us, we are all made of star stuff.
Hey, 6th graders. Welcome to Baggy Lab Day. This is a day that we all look forward to doing in 6th grade, but we know that you are at home. And so I'm going to walk you through how to fill out the paperwork for your Baggy Lab. We're going to be watching we're going to be measuring materials for it, and I'm going to let you copy down all the data that I have. So to start, the Baggy Lab is put into existence for us today so that we can prove the law of conservation of mass. The law of conservation of mass states that matter cannot be created or destroyed, no matter what happens to it, whether it goes through a physical change or whether it goes through a chemical change. Today I'm going to use a closed system, this Ziploc bag, and I'm going to cause a chemical reaction to happen inside this bag. And when I do that, I'm going to make sure to close it shut and prove that no matter what changes it went through, it's still going to have the same amount of mass it did at the beginning as it does at the end. Just watch. First, let's talk about the physical properties of the materials that I'm going to use. First on the list on your second page is baking soda. Now you can see I've already made a little bit of a mess of it, but I'm doing this so that I can show you what baking soda is like. Some physical properties of it is that it is a dry, white, solid, and very fine powder. And trying to get that into focus, if enough light shines on this, it somewhat sparkles. As those grains are very, very fine, it's sometimes hard to clean up. On the flip side, we have calcium chloride, CaCl2. This is a de-icer product for in the winter. When we want to get rid of the ice, we can lower the melting point or raise the melting point lower it, so that our ice will melt with some extra help from this material. As you take a look, it's also a dry white powder, but it's in the shape of Dippin' Dots. And it's, instead of being sparkly, it's very chalky in nature. And I'm just gonna put some on the table here for you to kind of get a glimpse of what it's like. Now, these two powders, they don't have a lot of action to them except when they mix. But because they are both dry powders, I can put them in the same bag and nothing is going to happen to them until I use a liquid. This liquid is water mixed with our very own bromothymol blue powder. This might look familiar to you because I use this for dry ice day. When I added dry ice, which was carbon dioxide, into the bromothymol blue, it started to change color. And that's just exactly what it's supposed to do. It's supposed to indicate if there's a chemical change. So if we see a chemical change today in the bag, you're going to see blue turn to a different color. So I'm going to use that to help the two powders mix together and create a chemical change. So I hope you had a chance to write down the physical properties of those three materials that I'm putting into the bag. Those are the main ones that we need to keep track of. Some other questions that I'm going to see you answering is, why was mixing the two powders a physical change? Well, I'm going to show you just that. I'm going to put a spoonful of baking soda and a spoonful of calcium chloride together in this bag. Nothing's going to happen. So with that being said, add my spoonful of baking soda, add my spoonful of calcium chloride. And just as you guessed, they're just hanging out in the bag as a mixture, but there's nothing that's causing that chemical reaction. Now, before I add my liquid to it, I want to know exactly how much mass I'm working with. So I'm going to measure this, and I'm going to write the equation for how much the baggie, the calcium chloride, and the baking soda are, and then I'm going to measure how much mass the bromothymol blue and the test tube are, because I'm going to lock them all into the same bag, and we'll compare before and after amounts. All right, so it turns out that when I put the baggie on, 28 grams. I need something to hold my test tube upright, so I put this empty beaker on the balance, which I'm going to zero out to make it seem as if there's nothing on there. I'm going to take my test tube of Be Blue, set it in there, and it shows me that I have 30 grams of the test tube and the Be Blue. All right, I've added it to the board. We have our test tube and our Be Blue that is 30 grams added to the 28 grams. So the total amount of mass that I'm working with is 58 grams. You might be wondering why I kept the test tube in play. Well, here's the scoop. If I were to dump the Be Blue right into the bag, then the chemical reaction would start happening before I could close this and make it a closed system. But I want to make sure I shut it before the chemical reaction happens. That means I have to include my test tube in the total mass. So I'm going to slide this down in there and carefully keep it upright while I close this. Now, total right now in my hand is 58 grams. Next up, watching the chemical reaction take place. Get ready, because with your notebook and adding your data to it, we're going to write down physical changes, and we're going to write down signs of a chemical change that are happening in this bag. just to let you know ahead of time. What are some signs of chemical change? If you see anything bubbling and fizzing, if you can hear some energy in there, if it turns a different color, if we feel heat or cold changing in the bag, we all know that those are all situations that require energy to happen. And when energy is given off, we know that we have a chemical change existing. Here goes. So I'm going to tip the blue liquid, allowing the two powders to mix. The blue liquid really doesn't do anything, but the powders are in charge of this chemical reaction. What do you notice? A lot of fizzing, a lot of bubbles. The color is no longer blue. And if you were here to feel this, this is pretty hot because of the chemical reaction that's happening in place. My bag was flat. There wasn't very much air in here, and now those bubbles are popping, filling up the bag. But good thing I have a closed system, so I can keep track of just exactly how much mass I have in here, not letting any of it out. So I'm going to be here kind of helping this chemical reaction happen with the test tube in the middle of it. This bag is getting pretty tight. Usually it doesn't pop. Let's hope that it doesn't. Probably won't. Some things you should be writing down in your yellow sheet. Physical changes that we saw. Well, we saw that there's a change of state. So our solids are now part of a liquid material, and that's a physical change. But all of the chemical changes that we have here, look at this. This is full of a gas, and that is a physical change. Sorry, that is a physical change that happened, changing a phase of matter. But a sign of a chemical change is when you have that bubbling and fizzing, when you have that change of color. My test tube is stuck right here. Can't hear it, but there is still a lot of energy in this bag. Still feeling the temperature change going on as well. But the big reveal is when we set this on the balance, how much mass is it going to have? What's your guess? Let's find out. All right, the final answer was that the mass was exactly the same in the bag before as it was after. So the after amount was, once again, 58 grams. There's so many other situations as well, such as when you burn wood in a fire and it turns into ash and embers and smoke. Seems like there's not much left at the end of that fire, but it's all turned into new materials. If we were able to keep all those materials as a closed system like we did today and measure it again, it would still be the same amount of mass. So today, just to wrap this up, we use the Baggy Lab to prove the law of conservation of mass, that when we cause materials to go through a chemical change, it still has the same amount of matter, even though it went through a lot of changes itself. On the data on the back, you're filling in what were some physical properties of those materials, what were some physical changes that you saw happening in the bag, and what were some chemical changes. You can write signs of a chemical change in that column. Don't forget to answer the questions on the back side.